everyone. Today we are hosting Professor Blank, who's a cognitive scientist and an assistant professor of psychology at UCLA and jointly in the Department of Linguistics. He received his PhD at MIT and did his postdoctoral training at McGovern Institute for Brain Research. His research focuses on functional neuroimaging, behavioral methods, and large language models. His research is basically focused on studying how different information sources are combined and how different cognitive processes interact during language comprehension, both in biological and artificial minds. So let's give him a good welcome and have fun.
Thank you. So hi, everyone on Zoom and in the room. Thanks for having me. I'm just going to move this a little bit. Okay. I usually start this talk with some broad introduction to how transformers work, but I'm going to assume that in this group, everyone knows how transformers work. If at any point I say something that's unclear about that, just stop me and ask me. But in general, in my research group, we're interested in figuring out how language comprehension is made possible. What are the mechanisms of comprehension? So I like to call this understanding. If this would only work. Let's see. And usually we do a lot of this in humans, often scanning their brains, but recently we started doing this with language models. And historically, there's been a lot of work on language models, first about their understanding of syntax or sentence structure, and work on their presentation of semantics or meaning kind of lagged behind historically. And to this day, there is more work on syntax than on meaning, but we're interested in linguistic meaning in AI systems. And the reason we're interested in this is not for studying language models on their own. We're interested in asking whether language models, and specifically transformers, are good models of human language processing, and in what senses they are and in what senses they're not. I will mention in parentheses that asking whether language models are good models of human processing is not one question. It actually has multiple interpretations, and I wrote this small piece a few years ago about the different ways in which we can interpret that question. I will not address this in this talk. So my studies I'm going to talk to you about and the findings are kind of agnostic with respect to how we interpret this question. And some people say, these are great models of the human mind, and specifically language processing. And some people say these models have nothing to do with how humans work. And I think that even if you take this critique into account, which I think we should be critical about these systems, this kind of research program is important because, as we know, all models are wrong, but some are useful, right? And so language models, and especially transformers, can master language better than any other model we have in linguistics, right? They can give us a computational representation of virtually any sentence. We don't have other models that can do that, and that allows us to test our theories at a much finer resolution than we can otherwise. And so I think that warrants studying them, even for people who think that they have nothing to do with humans. So I'm going to talk about 3 studies that look at specific aspects of comprehension in language models. So the way I approach studying understanding in language models is not doing some big, super broad notion of understanding that is going to necessarily be very vague and not well defined. Instead, I break comprehension into these small chunks or constructs that we know from human psycholinguistics and human neurolinguistics. And for each of these, we take experiments that have been done on humans and we adapt them to LMs to see if we find the same signatures in LMs that we see in humans. And so the first one is about the relationship between meaning and syntax. And we're going to ask whether meaning influences the syntactic computations in LMs. The second question will be whether LMs have a human-like representation of a very basic aspect of meaning, who did what to whom in a sentence. And the third one is going to be about integration of language and something non-linguistic, specifically vision. And I'll ask whether visual information is used for what I call pragmatic-like inference, and I'll explain what I mean when we get there. Before I start with the first project, I want to make sort of a broad note about the types of language models that I'm going to use. And I'm going to use very small language models, so on the order of 100 million to a few billion parameters. And the reason is that I want to avoid superhuman language models. So I want to study transformers that are actually used by cognitive scientists as cognitive models, of human language processing. And so, as you know, transformers are trained on next-word prediction, and these are used as general language processors. So these smaller transformers, cognitive scientists take them and they use them as models of behavior. For example, they use them to try to predict reading times in humans that read text, or models of the brain. They use them to try to predict patterns of brain activity in humans that are exposed to language. The current transformers, right, the ChatGPTs and Claude and all of those, are not just trained on next-word prediction, right? They're further trained, you do instruction tuning, you do alignment with human preferences and all of that. These are not used as cognitive models of language in cognitive science. So I'm not going to use those. And even more importantly for me, this type of training, instruction tuning, and alignment with human preferences is non-linguistic information, which is fine, right? We learn language not just through linguistic exposure, we learn language in many, many ways, but I'm interested in models that are only exposed to linguistic information to ask how far can that get us in getting a system that is human-like. Right, so if you just train a system on next word prediction, how far can you get? And so, yes, we want models of human language processing. The other thing is that transformers that are too large, they provide actually a poorer fit to human data. So the smaller models actually predict human data better because bigger models over-memorize language, right? Our memory is limited. We can't memorize the entirety of Harry Potter, but ChatGPT can. So not a good model of humans. Plus, we can't access the internal workings, right, of ChatGPT, and a lot of what we do falls broadly under mechanistic interpretability, so we're looking inside, so we need access to the model. Does that make sense? Yeah, okay, good. I thought it was a question. Yeah, that was fun. Okay, good. All right. So let's start with the first project. Does meaning influence syntactic representation? So we're looking at the relationship between sentence structure in transformers and the role of meaning. Okay, so we know transformers know a lot about English syntax, right? But do they process syntax in a human-like way? Beyond the fact that they can produce text that looks very well formed, right? Aligns with rules of English syntax. Do they do it like humans? And we chose to focus on one very specific aspect of how the human mind processes syntax, but it's a very fundamental and deep one. And that's the question of when and how can meaning influence your syntactic computations. And historically, in psycholinguistics, there were two competing hypotheses about when meaning influences syntax and how. One was that the early stages of syntactic computations are autonomous. They're blind to meaning. They proceed without interruption from information about meaning. So in the very first stages, when you try to figure out the structure of a sentence, you don't care about meaning. You just care about things like parts of speech and something like that. And later on, meaning comes in. Becomes integrated. This is called syntactic encapsulation. It's the idea that the syntactic processes kind of live in their own capsule and you can't interrupt them and you can't penetrate them. The opposite hypothesis was that syntactic processing is immediately penetrable to the influence of meaning. So information about meaning can affect syntactic computations, can direct them. And from a lot of research on human behavior, it seems like the second hypothesis is the correct one. So syntactic processing in humans is not encapsulated, meaning can penetrate it from the earliest moments, at least the earliest moments we can measure with the tools we have. And this seems to be a very fundamental property of the mental architecture of language. So let me show you a couple of examples to tell you how we figured this out about humans. So if you look at a sentence like, we admired the architect of the house that everyone knows, this sentence is syntactically ambiguous. It has two potential structures, and those structures are about what that everyone knows combines with. One is, it's the house that everyone knows. But the other option is that it's the architect that everyone knows, right? So this sentence has two possible structures. Now I'm going to give you a sentence that has exactly the same structure, but with different words. We admired the architect of the house that spoke at the ceremony. So up until that, same parts of speech, right? So syntactically, it's just as ambiguous. That can be the house or the architect, but we know that houses can't speak, right? So in this case, meaning allows us to disambiguate the sentence and say, oh, it's the architect that spoke at the ceremony, even though structurally they're both ambiguous. Now the question is, how quickly does this happen, right? How quickly does meaning help you? And so to do that, what we can do is have people read a sentence word by word. And every time they're ready to continue to the next word, they press a key. So they see the first word on the left side of the screen, they read it. When they feel they're ready, they press a key, and then that word disappears, the second word appears. When they're ready, they press the key again, the third word appears, and so on. And we measure how long it takes them to press a key, and that's a measure of processing difficulty, right? If it takes you longer to press the key, it took you longer to process that word, it was difficult. And you give people a sentence like the defendant examined, and then you measure the reading time of the word by. So the whole sentence is the defendant examined by the lawyer was unreliable. And what you see is that people slow down here because when they get to this word, they understand that the defendant was examined by someone. And that is inconsistent with their initial beliefs where they thought it's probably the defendant did the examining. So the people get here, they're surprised, they have to revise their beliefs about the sentence and they slow down. And that's because this part is ambiguous between two meanings, right? The defendant did the examining, the defendant was examined. All right, so far so good. The critical thing is that we compare these types of sentences to sentences like the evidence examined, which have exactly the same structure if you ignore the meaning. And we measure how long it takes people to read by when they get here and they don't slow down at all. Even though structurally this sentence is just as ambiguous. And so the fact that people already at the first word after this don't slow down, we take it to mean that meaning influence their syntactic computations immediately and help them disambiguate this sentence towards the right structure, right? Because evidence cannot do the examining. It has to be examined by someone. So we wanted to ask whether we can find any syntactic computations in transformers that are blind to meaning. Of course, many of them will be sensitive to meaning because eventually meaning and structure have to combine, right? So there'll be a lot of things that are integrated. We wanted to see if we can find anything that is encapsulated from meaning, because if we could, that would be very different from humans. Okay, so we wanted to ask, are syntactic computations in transformers penetrable to meaning? And because of how transformers work, we made the following assumption. We said, if syntactic encapsulation existed anywhere inside transformers, we don't know if it did. If it did, that would be very different from humans. If it existed anywhere, then attention heads are the best candidates for it. We reason because the residual stream, the embeddings, they're very multidimensional. We already know a lot of information there gets entangled. But the idea is that maybe some attention heads learn to pay attention and link words in ways that are purely influenced by syntax and are not penetrable to semantics at all. So that was the idea. Maybe such attention heads exist. And in fact, previous research suggested that some attention heads learn automatically to specialize in identifying specific syntactic relationships between words. So there are some attention heads that really like specific types of syntax or syntactic relationships. For example, you can find a head that if you look at the attention that it pays from the verb, it usually pays the most attention to the subject noun more than any other word. So if you look at something like the author wrote a novel and you look at attention from wrote, the strongest attention is going to be to the subject, to author, less than to any other word. And it's not just a matter of proximity. You can do something like the cat in the garden chased the butterfly and look at attention from chased, and it's going to be strongest to cat and less to other words, even though cat is like farther away in the sentence. So we wanted to ask, are those attention heads really just sensitive to syntax, or can you modulate what they do with semantic information? So here's what we did. We tested 3 models. We tested BERT, which has bidirectional attention, right? So it sees the future. And we tested GPT-2 and Llama-2. They're unidirectional, right? So they're like humans. They can't pay attention to future words. They can't see the future. I'll mention later why we did both. I think they teach us different things. In each model, we first identified some specialized attention heads, and we follow previous literature in doing this. For example, a head that attends from a verb to the subject noun, a different head that attends from a direct object to the verb. So if you do something like, I gave the cat a toy, it would attend from toy most strongly to gave, or if it's bidirectional, from gave most strongly to toy, and so on. We had about 5 or 6 different dependencies that we found. And then we tested whether attention strength in these heads specifically, in these syntactic attention heads, is influenced by meaning. And the way we did this is to manipulate plausibility as one aspect of meaning. So we created sentences where that dependency that the head likes either makes sense semantically or doesn't make sense semantically. So we had pairs of sentences where one was plausible, one was implausible. For example, for a head that attends from a verb to the subject noun, we had sentences like, the cat in the garden chased a butterfly, where the dependency that this head likes between chased and cat is plausible, right? Cats can chase. But we also had sentences like the garden and the cat chased a butterfly, which is syntactically well formed, right? The structure is perfectly fine, but semantically it doesn't make sense because gardens don't do chasing, right? So it's this dependency that doesn't make sense. And our hypothesis is if this attention head cares about meaning and is not purely syntactic, then it should pay a lot of attention from chase to the subject here, but less attention from chase to the subject here because this is implausible. So if we find a difference in attention, despite these two sentences having exactly the same structure, this tells us that there is some effect of meaning here. And so let me show you what we found in GPT-2. On the y-axis is the attention strength for plausible sentences from the verb to the subject versus implausible sentences. And we see a significant difference. There is less attention when the subject is implausible. And we find this in all the 5 dependencies that we looked at in GPT-2 of passive verb and a subject, a direct object and a verb, an object and a preposition, an adverb and a verb. In all of these cases, it holds. It holds in 3 out of the 5 cases. In 2 of them, it didn't quite work. And in Llama 2, it worked in all of the heads. Since then, we found more heads, and it works in the vast majority of them. So that suggests that these attention heads that like very specific syntactic relationships actually also care about meaning. There is one comment here that we might make, which is that this is not actually about meaning. This is just about frequency of exposure. So if you took the corpus that these models were trained on, whatever corpus that is, that corpus probably contains some examples of cats being the subject of chasing, but it probably never includes any examples of gardens being the subject of chasing, right? So it's the model pays less attention from chase to garden because it's never seen a sentence where garden is the subject. So I have 2 comments or 2 replies to this. One is all the knowledge that language models have comes from exposure to forms of their distribution, right? Like how else would you learn probability? That's the only input to the model. So that's one thing. The other thing is that we actually tested this, and frequency of exposure drives this effect in part, but not completely. And the way we looked at this is we created a 3rd class of sentences that were plausible but surprising. So the relationship between the subject and noun was plausible, but was very, very surprising, meaning the model was not exposed to it a lot. And by using that condition, we were able to dissociate frequency of exposure from plausibility. All right, so what are these attention heads doing, right? They have a fixed amount of attention. If they pay less attention to their preferred dependency, they have to put that attention somewhere else, right? Because the attention has to sum to 1. So one option is, well, they just take whatever attention is left and they just spread it uniformly across all the other words. But we thought maybe something else is happening. Maybe the attention head is in effect searching for a better word. So if the subject is not a plausible subject, maybe the attention head is putting some attention on a different word that could be a good subject. And if you look, for example, again, at this head that attends from a verb to a subject and the implausible sentence like the garden and the cat chased a butterfly, we build the sentence intentionally such that there is this word here that we call it a lure because syntactically it's not the subject, right? It's an incorrect dependency, but semantically it would be a good subject, right, to do the chasing. So that's why it's a lure. Syntactically, it's not the correct target, but semantically it could be. That doesn't happen in the plausible sentence. So if you look at the cat in the garden chased the butterfly, this is not a lure because syntactically it's not the subject, semantically it couldn't be a subject. And so what we thought is if the attention head is kind of looking for a good subject, we should see more attention from the verb to the lure in the implausible case and less attention here. And it doesn't always happen, but in 8 of the 11 cases that we tested, that pattern did hold. So at least in some cases, it seems like what's going on is that some attention goes to a different word that could be a better candidate for that syntactic dependency, even though it's not in the right place. I will mention that this, in a hand-wavy way, mimics what humans do. So we have a lot of studies that when humans get a sentence that is not well-formed or doesn't make sense, they try to infer what the person meant to say. So they interpret the sentence often non-literally. And you can think of what the models are doing here is the same. They sort of maybe assuming or inferring that the sentence has some noise, right? That the sentence was corrupted and saying, well, maybe the subject is somewhere else in that sentence. So what we see is sort of, right, these attention weights are like gating mechanisms, right? They determine how much information flows from different words to a target word. And so if you think of this as the verb, right, and there's some information that flows from the cat and some information that flows from the garden, this attention heads let a lot of information flow from cat to the verb, even when cat is not necessarily in the position of the subject, because semantically it's a more plausible subject than garden is. All right. So we asked whether syntactic computations in transformers are penetrable to meaning. The answer seems to be yes. We didn't look throughout the whole transformer, but again, we figured out that attention heads that are specialized for syntactic dependencies are the best a priori candidates. If there was encapsulation anywhere, we thought it would be there, and it's not. And I think this is a very strong test of encapsulation, not just because these syntax specialized attention heads are the best candidates, for two other reasons as well. One is that in GPT-2 and Llama 2, because they are unidirectional, the effect happens at the critical word, right? So it reads the sentence word by word, and it gets to the verb, and there we see an effective attention to the subject, right? For example, or it reaches the adverb, and then we see attention to the verb before it sees future words. And that's exactly how we measure immediate effects in humans, right? We do the evidence examined by, and we see the effective meaning already here. And that's what we call immediate effects. So we kind of see something parallel, more or less, in transformers. So that's from the unidirectional models. From the bidirectional models, I think we also learned something. For BERT, the sentences are unambiguous because BERT can see the whole sentence, right? There's no temporary ambiguity. In all the human studies, the sentences always start as ambiguous because that's how you see if meaning helps you, right? You give a sentence that is in principle ambiguous, and then you show, look, people rely on the meaning to disambiguate it. BERT gets sentences that are completely unambiguous, so it doesn't need to rely on meaning for disambiguation. In the human studies, you might say, well, you give people an ambiguous sentence, so of course they're going to rely on meaning, but maybe they don't rely on meaning usually. Maybe they only rely on it when the sentence is ambiguous. BERT sees sentences that are unambiguous, meaning still has an effect. And I think that shows that this penetrability, that syntax is penetrable to meaning, is inherent to how these attention heads work. It's not just optionally triggered if something is ambiguous. All right, so why don't we see any encapsulation? There's a computational reason for this. The idea is that encapsulation is very advantageous and helpful if you're working in a domain that is unambiguous. If you have a domain where it's very clear how to solve a problem, then you don't want any external interruptions, you don't want any external information to bother you, you're just doing your task and solving it. Now, transformers need to predict the next word, right? That's a problem that they're trying to solve. If you're trying to predict the next word in language, it's very useful to rely on syntax, but syntax is pervasively ambiguous in language. Syntax is extremely ambiguous, and so meaning can help you. It's good to rely on meaning as soon as you can, because it helps you to quickly resolve the indeterminacies, right? You don't have to make an assumption about the structure and only later on track back and revise what you thought. If you rely on meaning from the get-go, you're less likely to make mistakes. So I think what we conclude from this study is that we found some fundamental aspect of computation that is very similar between these language models and humans, which we think is kind of cool. So that was the first study. The second study is about whether transformers have a human-like representation of who did what to whom in a sentence. So do the transformers understand the language they use? And so there are a lot of claims that transformers understand, right? Especially in the industry, but also in some circles of academia. So, right, so the Google engineer who thought the company's AI has come to life 44 years ago, artificial intelligence is now an A+ law student, right? Or the case that AI is thinking and so on. To ask, do transformers understand? We need to think about what we mean when we say understanding. So a lot of the work on thinking and or understanding in language models looks at things like logic, right? Can they reason logically? Do they have common sense, or these intuitive theories, understanding of how the world works? Do they do social reasoning? Can they solve analogies? Do they have these event schema, these templates of how events work, and so on? These are all extremely important aspects of understanding, but these are aspects of thinking, not language. And thinking and language are not the same thing. So we wrote this piece that was led by my wonderful colleagues, Karl Mahawald and Anna Ivanova, about dissociating language and thought in large language models, if you're interested. The gist of this is based on what we know from cognitive science, from psychology and neuroscience. And the idea is that we know that the human mind and the human brain has a system that only does language. It's specialized for language. It doesn't engage in thought. It doesn't care about logic or social reasoning or music or arithmetic. It doesn't even care about programming languages. Those are not the same as natural languages. It only cares about language. And so there is a dissociation between linguistic processing of a sentence, processing it in terms of language, and then subsequently later using the content that you extracted to do reasoning. Those two things are not the same. They're two different steps. And so it's very important to test whether language models can think and reason, but it's also critical to assess transformers not just on thought, but also on aspects of meaning that are more purely linguistic. And it's very hard to draw the line in a sharp way and say, this is linguistic, this is not. There are things that are very clearly linguistic, there are things that are very clearly not, and then there's a huge gray area in the middle. But we tried to look at for some aspect of meaning that we thought is as close to purely linguistic as you can get. And what we chose is who did what to whom in a sentence, who the agent is and who the patient is. So if you look at a sentence like a prisoner pulled a doctor, it's not just a bag of words, right? There's an agent, the prisoner is doing the pulling, there's a patient, the doctor is being pulled, right? This is very different from a doctor pulled a prisoner where the words are the same, but the roles are reversed. Right now, it's the doctor that is the agent that's doing the pulling and the prisoner that's being pulled. And you don't even have to focus just on active sentences. You can take a sentence with a different structure, like a doctor was pulled by a prisoner, where here the doctor, even though it's the first word in the sentence, it's not the agent, it's the patient being pulled, the prisoner is the agent, right? So you can have sentences with different structures, but the same event roles, or same structure and opposite event roles. So the question is, once you figure out the structure of the sentence, how do you get to the meaning of who did what to whom? So these event roles, or thematic roles, as some people call them, they're a very basic or simple aspect, right, of mapping syntax onto meanings. This is sort of the first thing you have to figure out once you figure out the structure of the sentence, right, is knowing who did what to whom. And they're central in psycholinguistic theories of sentence processing, which is why we chose to focus on that. So they're a very big and important aspect of meaning. And we asked, how are event roles represented by transformers? So our approach, originally when we started this, we took inspiration from fMRI, an approach that's called multi-unit pattern analysis. You might be familiar with it by a different name, because when we started doing this in parallel, people started doing the same thing in LM land, but not inspired by fMRI. And with a different name. But basically what we're doing is we're comparing different embeddings to one another and computing the similarities between them. That's it. So we can take a sentence like a doctor pulled a prisoner and look at the residual stream and just get the embedding of that sentence. Now we want a representation of the entire sentence. So we tried a bunch of things. You can either take the embedding of the period at the end of the sentence, or you can average the embedding of all the words. Or if you're looking at Bert, you can take the representation of the verb, because Bert sees the whole sentence. We get the same results regardless of which method we try. So I'm going to show you one of them, but the results are all the same. And so let's say that this is the representation of the embedding. Each of these is like an artificial neuron or an entry in the embedding. And the brighter it is, the more active it is, but I'll just show it in colors for the purposes of illustration here. So this is my embedding of that sentence. Separately, independently, not after, just completely independently, we feed a different sentence, a prisoner pulled a doctor, and we extract the embedding. And all we want to do is compare them, right? So basically compare these vectors, which visually means, are these the same colors or not? But mathematically, it's just comparing vectors, right? So we compute the similarity of these embeddings with a cosine angle. That's all we do. But the way we build our stimuli is that they come in triplets. And in each triplet, we have a third sentence, like a prisoner was pulled by a doctor. And the idea is that in a triplet, two items have the same meaning, but different structures, right? Active, passive, but in both of them, the doctor is doing the pulling. And another pair has the same structure, but different meaning, right? So both of them are active, but the roles are flipped. And the critical test that we do is very simple. We want these to be more similar, right? Two vectors of a sentence with the same roles should be more similar. So the critical test is that sentences with the same event roles should be represented more similarly than sentences with opposite event roles. Does that make sense? That's the whole analysis. All right. Now, critically, we used sentences that are reversible in the sense that both doctors and prisoners can do the pooling, and there is no a priori bias or heuristic as to which is more likely. So you can't use tricks, right? If we did something, the dog ate a bone and the bone ate a dog, like, of course, the dog ate a bone, the dog is doing it, right? So we use sentences where you can't use these tricks. And like before, we're testing these smaller language models. Now, we also wanted to compare this to human data. Now, of course, I can give you two sentences and ask you, are the event roles the same or are the event roles different? And you can all answer that question perfectly. But we wanted to see whether human intuitions about similarity, because what we're measuring is similarity between embeddings, right? We're not asking the language model with a prompt, who is the agent? So we wanted to see whether human intuitions about similarity reflect event roles, even without cues to plausibility, right? So in our materials where doctor and prisoner can both do pooling, when you don't give humans explicit instructions to focus on event roles or to focus on structure, and when they're not that motivated to carefully contemplate. And so what we did is we recruited UCLA students and we gave them pairs of sentences and had them rate similarity on a scale from 0 to 100. UCLA psychology students are always motivated to finish as quickly as possible and pay as little attention as they possibly can. And they only saw one single pair that had the same meaning and different structure, and one single pair that had different meaning but same structure. And these came from different sets. So if this was a doctor and prisoner and pooling, this was like, I don't know, a lawyer and an architect and insulting or whatever. And we hid these two pairs among filler pairs. So these are pairs of sentences that are not about event roles, don't require close attention to sentence structure. They're very easy to answer. It's like, you know, a boy bought a sandwich and a girl ate a cake. Those are similar versus something like, you know, the octopus hid in the sand versus something like two astronauts, walked on the moon or had a cough or something, like things that are clearly very, very different. All right, and note that we didn't ask LMs to explicitly rate similarities. We didn't give them a prompt, sentence A, sentence B, give me a number, because we don't want extraneous stats demands, right? We don't want to assume that LMs, especially these small ones, understand the prompt, understand what the word similar means, know how to apply the concept of similarity to sentences. We want to look inside. All right, so let me share the results. In humans, similarity is on the y-axis. We have sentences with the same meaning in blue or different meaning in red. This is the similarity of sentences with the same meaning. This is the similarity of sentences with opposite meaning. So even without plausibility cues and even without instructions to focus on event roles, people have the intuition that sentences with the same meaning are more similar than sentences with opposite meanings. Good. All right, so now GPT-2, I'll show you the last layer. All the layers show the same pattern. I know for studies of meaning, it makes more sense to look at middle layers or middle to last layers. They all show the same pattern. So I'm going to show you similarity, cosine angle. This is the similarity of sentences with the same meaning. Sentences with opposite meaning are more similar, which really surprised us, which is why we tried to represent sentences in many different ways and look at all the layers and look at different models. And in all the four models that we looked at, in all the layers, we find this pattern, which we really did not expect. And it seems like the similarity in transformers in the residual stream is governed by structure, not by meaning. These sentences are more similar because they're both active. This is active versus passive. And so it seems like syntax has a really strong influence. So it's like this transformer knows that there's a doctor and knows that there is a prisoner, but unsure who's doing the pooling. All right, so then we thought, okay, you take two embeddings from the residual stream, that's like hundreds of dimensions, right? Or thousands of dimensions. They have to capture a lot of information. Maybe there is information about event roles, but it's just hidden in a small subspace, right? It's not, and when you compare full embeddings, you wash out that information. Because maybe for whatever reason, syntax just captures more of the dimensions. It doesn't mean that the event roles aren't there, right? They're just in this small subspace. So what we did is, to do this, we used now stimuli that are more complex. We used sentences that had 12 structures times 2 meanings. So instead of each set being a triplet, each set of stimuli had 24 sentences. So the 2 meanings are flipping the agent and patient, but sentences went from things like the doctor delivered the prisoner a gift, all the way to it was the gift that was delivered to the prisoner by the doctor. There were 12 different syntactic structures varying in complexity. And what we did is we just did probing, or what in fMRI we call pattern classification, but we all know this is probing. So basically what we did is we took pairs of same meaning sentences, so two sentences with different structures that have the same meaning, and we either subtract them or we concatenate them. We try both, doesn't really matter. And then we take a pair of different meaning sentences that have opposite agent-patient, and we subtract or concatenate them, and then we just train a linear SVM on these subtractions or on these concatenations to tell us whether this input comes from a pair of sentences that have the same meaning or a different meaning. So we're basically asking, is there any subspace in these vectors that can tell you if they both came from sentences with the same meaning or opposite meaning? And then we test on new pairs, and the new pairs are always unseen syntactic structures. So we have 12 structures, we train on 10, we test on the other 2. And what we find is that we can find significant decoding, right, or significant performance, but the accuracy is very, very low. So chance is 50%, and we get like 55%, or like at most 60. So nothing that impressive. We had only one layer in only one model that has accuracy of more than 65%. And even in this layer, you see very large variability across the test fold. So depending on which structures you're holding out, it can be 100% accurate or it can be 33% accurate. So unclear what's going on there, and it's one layer in one model. Yeah.
So you mentioned the 12 structures. Are there, if I'm going to talk about in terms of edit distances across the syntactic structures, is it very variable, or are they like I want to say if you're just changing the voice or if you're just changing? So
we changed 3 things. We changed active passive. We changed direct object or prepositional object. So the doctor delivered the prisoner a gift, or the doctor delivered a gift to the prisoner. And we changed whether there was a cleft or not. So whether it started with it was the blah, blah, blah. And we did all the possible combos of all these 3 different things.
Pretty exhaustive in terms of what you can do.
Yeah. And these are probably like the 2 most different ones that we have. So that didn't quite work. Like maybe there's something there, but not in any impressive way. And it doesn't seem close to humans still. And so then we thought, okay, so it's not in the residual stream, but what happens with attention heads? Maybe there are attention heads that can very strongly identify agents and patients. And it turns out that there are. I'm going to show you one attention head in BERT that looked really, really nice. I'm going to show you attention strength from the verb to the agent or the verb to the patient. We did it in BERT because, as you saw in other sentences, sometimes the agent comes before the verb or after the verb, and the patient can come before or after. So we need bidirectional attention. And so here is the average across 50 stimuli for one syntactic structure. So it pays more attention from the verb to the agent than the verb to the patient. Here are all the other syntactic structures, and in the red is the average. So in all of these cases, this attention head pays more attention from the verb to the agent than to the patient, regardless of the structure of the sentence, regardless of whether the agent comes before the verb or after the verb, before the patient or after the patient. In the same head, you can look at attention from the object to the agent or the patient. So this would be the gift. And on average, not as clean, but on average, more attention to the agent. And you can even just look at attention from agent to patient or from patient to agent. And again, you get a very strong pattern, more attention from patient to agent. So this attention head really robustly distinguishes agent from patient across sentences with very different words and different syntactic structures. So it's there in the attention heads, but it doesn't make it to the residual stream. So do transformers understand who did what to whom? This is a very simple task of understanding. We find that LLMs have the capacity to extract that information, right? Because it's there in attention heads. But because of what we saw in the residual stream embeddings, it seems like this information doesn't get any prominent role in sentence representation, in contrast to humans, right? So there are attention heads that pull it out, but then it kind of gets washed out in the residual stream. One thing this shows you is that knowledge of syntax doesn't guarantee semantics, right? Even these small language models are pretty good at English syntax, and yet they kind of don't represent even this very basic aspect of meaning. So what's happening here? There's 3 possibilities. Not all of them are on the slide. One way to think about it is, well, LLMs are trained on next word prediction. So let's think about how we can use event roles for next word prediction. In real language, if you take a real corpus of language, often plausibility and common sense suffice to figure out who did what to whom, even if I give you a bag of words. You can just use those heuristics. And so it makes sense that the transformers probably learn to use those heuristics to figure out who did what to whom, right? Because it's very useful. And so maybe event roles aren't elevated in the residual stream when you take out these constraints on information, right? These plausibility cues. Because our materials didn't have any heuristics or cues. And maybe when you take those out, the information just isn't elevated. So that's one option. The second option is that event roles are represented, but in a very specific way that is tied to specific verbs. What do I mean? In our probing analysis, we have many, many different sentences with many, many different verbs, right? So there's pulling and insulting and chasing and giving. Maybe the LM has a concept of puller and pullee, but that's different from the concept of chaser and chasey or giver and givey or insulter and insulted. So maybe the roles are there, but they don't generalize across different verbs. They're sort of very fine scale roles. And so we're still testing that now, so I don't have an answer. The third option is that the event roles are there, but they're washed in the residual stream because the residual stream is interested in next word prediction, right? So you compute it, but you don't need to represent it as such in the residual stream. You just need to extract information from it and use it in a way to push concepts around vocabulary space to make next word predictions. The last option is that event roles are represented non-linearly because our probing classifier was a linear SVM. Totally possible. And if that's true, I think it would be very interesting. I think it would be an important exception because many types of meaning of semantic information are represented linearly, including gender and sentiment and even plausibility, right? So it would be very interesting if plausibility, just figuring out whether a sentence makes sense or not, you can extract linearly, but who did what to whom you can't. That would be kind of an interesting exception. Now, I think this is important because these embeddings from transformers are used to predict brain activity during language processing, right? So I'm not saying transformers could never understand who did what to whom. In fact, I think it's very likely that the larger models that we all use definitely understand that. It's these smaller models that seem to struggle. But these smaller models are what people use embeddings from to predict brain activity. And I think what this study shows is that whatever brain activity we're predicting, it can't reflect event roles, right? It can't reflect even this very basic aspect of compositional meaning, of sentence meaning. And that's important to know, right? That what we're predicting in brain activity is probably something just like lexical semantics, like meaning of individual words or something. The other conclusion from this study, which we are not the first to make, is that it's vital to test the ability of transformers to understand language, right? Not just reason and think. And you need to do this with carefully controlled materials inspired by psycholinguistics, right? So the way we took plausibility cues out allowed us to figure out that without plausibility cues, the representation of who did what to whom is kind of crappy. All right, so in small language models, learning to predict the next word is sufficient for learning what event roles are because attention heads extract them, but maybe it's insufficient for representing event roles like humans and giving them a very prominent role in the representation of the sentence. So that was project number 2. The last one is about whether visual information is used for making pragmatic or non-literal inferences. So let me start. Yes.
That's a quick question.
Yeah.
What other ways would there be to measure this sort of level of understanding, right? Like presumably, sometimes we get lots of either fill in yes or no or whatever. Small language models. So is there?
You might.
Is that true actually? Even in these models?
Yeah, it's a good question. I think it really depends on how you set up your materials. You can try to, so there are several ways I can imagine going about doing this. One is things like looking at next word prediction. So things like the waiter gave the customer the versus the customer gave the waiter the, right? So the waiter gave the customer, you'd expect high probability for burger or meal or whatever, or bill, but the customer gave the waiter is something like tip, right? That would be very useful, but it doesn't tell us how it gets there, right? And so then the embeddings are still important to see, well, does it represent those roles? Maybe it does, but not in the way we think it is, or we think it does. The other way is to do use specific verbs that create expectations about whether you're going to refer to the agent or the patient. So, for example, if I say the doctor frightened the Baroness because it's probably going to be because he, assuming the doctor is a he, right? So we're using the bias that LLMs have. But the doctor feared the Baroness because it's a she, right? So he feared her because she did something. So you can use those to sort of maybe see, right, if the model, assuming that it knows these expectations that verbs create, if it can figure that out, maybe it can. So that's a way to see if at the like by the time you get to the output level, whether there's something that looks like.
I mean, I was just thinking of frankly just asking.
Oh, you could, yeah. I haven't tried. Yeah, I haven't tried it because there, GPT-2 is like not very. We were impressed in the back of the day at how good it is, but it's not that good, right? So you can do things like the key doesn't fit in the suitcase because it is 2, and it doesn't know if the word is big or small. So like, who knows, right? But it's worth trying.
Have you tried with the larger words?
No. I was not motivated. By the time we added the 2 bigger models, that student wanted to move on to a new project, and I was like, okay, let's just get this out. So it was not because it wasn't interesting. Yeah, exactly. It's like, get me an undergrad who wants to do this, and we'll do it. All right, so I'll start with the demo. Let's say that you see this array of objects, and you're playing a game with someone else. I'm telling you a target object, and you need to tell this other person to make them point to the right object. So let's say I tell you that this is the thing they need to point to, and you need to tell them point to the, and make sure that they point to this. What would you say? Point to the cork, right? If you said point to the cork, they'd probably get it right? What if you need them to point to this? What would you say? Point to the big hammer, right? This is big too, right? Why did you say big here? Because you didn't need to, right? So the reason people say big here is because this hammer is part of what we call the contrast set, right? There's a contrast in size. Saying just hammer is underinformative. You need to say which hammer. And so speakers are very cooperative. Human speakers, they are only as informative as they need to be. So they're not underinformative. They wouldn't say hammer because then it's unclear. But they're also not overinformative. They won't say big cork because what's the point, right? Cork is enough. So that's on the speaker side. But what's interesting is that listeners are very sensitive to this. So comprehenders use the visual context to make rapid inferences about the intent of the speaker. And these are pragmatic inferences because they are non-literal. So for example, if you see this and you hear click on the big, we can measure where people move their eyes when they hear big before they hear the name of the object, just from the word big. And we see that people look more, they fix it more on this than on this. We call this a pragmatic inference because literally they are both big, right? So literally both of these are likely to be described by the word big, but pragmatically, if we think about the speaker's intention and if we think about the speaker wanting to be cooperative, we can make a very rapid inference to think, well, if they wanted to say this, they would just say cork. If they're saying big, they probably mean this. And so the question is whether vision language transformers integrate visual and linguistic information for these inferences that are pragmatic-like. I'm calling them pragmatic-like because I don't want to say that language models reason about the user that inputs text and what they're going on in their mind and what they intend. So it's pragmatic-like. But can we get a signature that looks like this? So our approach is to take off-the-shelf vision language transformers. So those are not just trained on expert prediction, they're trained on following instructions because they're off the shelf, but that's what we could take. We feed them an image and a partial instruction. So for example, we give them the text in the image point to the, and we either give them an image like this, so that here there's a contrast, or an image like this where there is no contrast, although there is a big thing and a small thing. And what we want to see is whether the LLM predicts that or the VLM predicts that the next word is going to be big. And so saying big in this case would be felicitous, right? You want to say big because if you just say hammer, it's unclear which one you mean. In this case, we say that it's infelicitous, right? Because why would you say big? You can just say hammer, even though syntactically it's fine and in the literal sense, it's fine. So it's just pragmatically infelicitous. And so we extract the probability that the transformer assigns to big as the next word, right? So the probability of big from the last vocab layer, given the instruction of the image. And we want to ask whether the transformer is more surprised when the word big appears here than here. So to see this, we just convert this from a measure of probability to surprise, which you're probably familiar with, minus log 2, that's called surprisal. So higher means the model is more surprised. All right, so in the image point to the, that's what the model sees. It doesn't see the word big, we extract the next word probability of big. And so in this case, the model should not be surprised. In this case, we expect higher surprisal. And so in lava, I'm going to show you surprisal. This is the surprisal in these types of images. And in these types of images, we get higher surprisal. In struct blip, a different model, we get the same pattern. Cool. Then we asked, okay, what comes after the word big? So this already was exciting to us. This is like, oh, this kind of looks like a pragmatic style inference. Then we said, okay, what word comes after big? Let's say we gave it the input in the image point to the big. In both cases, the next word has to be hammer, right? There's nothing else you can say. So then we fed in the image point to the big and we extracted predictability of hammer. And what we saw is that the model is more surprised here than here. So it's sort of still carrying this pragmatic surprise in both models. And these are, we now have 960 of these points. It's just like an old plot. The reason I'm mentioning this is because then we figure out that this has an alternative account. Not the big. The result for the surprisal of the word big really seems pragmatic, but the surprisal for hammer has an alternative account, which is in this image, there are more hammers and they take more space in terms of pixels. So the word hammer is less surprising. And in this image, there are fewer hammers and they take less space. So hammer is more surprising. And so this can just reflect something like object frequency, right? How many of them are there, or object area, and not about pragmatics at all. So to test this, what we did is we changed the sentence so that the instructions are felicitous or underinformative instead of overinformative. What we did is give these images with the input in the image point to the, and then we extracted surprisal of hammer without big. And we also wanted the period because otherwise you can say in the image point to the hammer, that's big, or point the hammer, that's bigger. So we wanted to make sure that we sort of extract the probability that the sentence ends here. And in this case, the pattern is flipped. Now this is surprising, right? Because this is underinformative, which hammer? And this should be, so pragmatic says this should be more surprising, and pragmatic says this should be less surprising. Object area still says the previous prediction that here hammer is more expected, right? Not more surprising because there are more of them. And so what we find is that the model is actually now more surprised in this case than in that case. So it behaves pragmatically, not in terms of object area and frequency in both of these models. Okay, I'll skip this. This is just to show you the pattern flipped between the two experiments. If you say the word big, it looks like this. If you don't say the word big, it looks we ran many experiments. I think by now we have like 12 or 13. It seems like next word predictions are very sensitive to the frequency and area that objects take in the image. And this sensitivity can really drown out the pragmatic effects. So we think the pragmatic effects are there, but they're so subtle that if you don't design your stimuli very carefully, this confound is just going to move things around. I'll show you two last things. Actually, I'll show you just one. No, I'll show you two quickly. We did a language production experiment. So we gave an image and we gave a very long prompt, like I gave you. You're playing a game with a user. You need to say something so that they know which object to pick up. Return a brief phrase that describes the object on the left side so the user knows which one of the objects to point to, blah, blah, blah. There are a lot more instructions. And we give either this image or that image. And we measure how often the output of the model has a size adjective. And when there is a contrast, in most of the responses, the model would say big or small, depending on which one. And when there is no contrast, it almost never says big or small. We wanted to make sure that this is not just about verbosity, like maybe when the image is more complex or ambiguous, the model just says more in general. So we looked at color adjectives, and it's the same in both cases. So it's not like the model speaks more in that case. It's specifically that it says more informative things. All right, so if you hear in the image point to the big, and you predict that it's going to be hammer and not cork, in this case you wouldn't know, right? It could be hammer, there are two of them. It could be cork, there are two of them. What's the mechanism, right? What causes next word predictions to be pragmatic-like? And we thought maybe there are some attention heads that pay attention from the word big or small to the object that is in the contrast set and not the other object, just like visual fixations in humans. So the attention head is kind of like human eyes that pays attention to the right part of the image, right? So it hears the word big and it pays more attention to the big hammer and not the big cork. And so you know that attention heads can pay attention from text tokens to image patches. So let me show you what we found. We found 9 attention heads that pay attention in a pragmatic-like way. I'm going to show you one of them and just one example. So we gave images like this or images like this that have 2 contrasts or just 1 contrast. And if we do something in the image point to the, and we look at attention from the, at this point, it's unclear what it's going to be, right? And so attention here, more attention is in darker color. You can see it's kind of all over the image in both cases. Okay, but then what happens if you're doing the image point to the small, right? That's the critical thing. What happens to attention? In this case, attention goes only to the turtle, not to the small glove. And in this case, attention goes to both small things, the small turtle and the small glove, because they're both parts of contrast sets. So we thought that's really cool. We're now trying to do ablation studies to see if you remove these attention heads, that screw up the next word predictions, but we haven't done that yet. So next word predictions distinguish felicitous instructions from infelicitous instructions. The text production seems to be felicitous. So when we ask the model to talk back to us, it's not over or under informative. And attention heads predictively attend from the size adjective to visual objects that are part of this comparison class. So I showed you 3 things: that syntactic attention heads are sensitive to meaning, that small language models have this problem representing who did what to whom, and that we have these pragmatic-like differences in language models. And I know this was a lot, so apologies and thank you. Yeah.
So just given how like the visual tokenizers work with the LLMs in the first place, why did you pick like size as the primary adjective to test this rules? Or, like,
great question. The reason is that people are not equally informative for all types of adjectives. So for example, with colors, in some cases, people will say color even when they don't need to. So if there's a cup and a plate and a chair and a lamp and the cup is blue, people might say blue cup. And it's like there's just one cup. And so to test if this works like humans, we had to take a case where humans speak informatively, and size is like the thing that's been studied the most. You're right that for LLMs given tokenization, it's very bad. So we have a new set of stimuli with color. And actually, Alyssa Kreis discovered that in some cases of color, people are just as informative as they need to be. And so we tried to make materials based on her studies on those specific cases where people are informative. And we don't have results yet, but hopefully soon.
Wait, is that blue color example because there's only one blue item, or just mean like what blue item?
So it's because there is one blue item, and the theory is that it helps with visual search. So color is something that pops out at you. So if you take Spanish where you say cup blue, people won't say blue. So it really, they only say blue in languages where the adjective comes before, and we think that's because it helps with visual search.
So it's still pragmatic.
Yes, exactly. Yeah. It still seems to be very listener oriented. All right, cool.
I guess this is like a meta question.
Yeah.
Like why like you looked at both attention heads and embedded, and I wonder if you have a thought on like if you like the next study or whatever, like if you look at one or the other, it's sort of expect to find like
I think it depends on the theoretical question. I'm starting to like attention heads more. Both because they're, in a sense, they're easier to interpret, right? Like less is happening compared to like 1,000 dimensions. But it really depends on sort of the part of the mind or the component of the process that we're trying to model. So like attention heads seem very similar to retrieval from working memory of past words. So whenever we want to look at something like retrieval or integration, it seems like attention heads are the right place to look at. The embeddings are mostly when you want like a representation of the whole thing, right? which yeah, I find a little harder to interpret. The one thing that we're gonna do with embeddings now, we're doing two things now with embeddings. One is when we're looking at multilingual LLMs and we want to find whether there are subsets that represent different languages and to what extent the overlap between different languages depends on like, are they typologically close or whatever. So that looking at embeddings is nice, right? You see units that like really like some language. And the other thing is we have some studies that try to sort of find the underlying dimensions that govern the residual stream. So not the actual dimensions, but like in the space, right? What governs the organization. So it's kind of like using sparse autoencoders, but we're not using sparse autoencoders, we're doing something else. So those are two cases where we will use embeddings, but I'm starting to like attention heads more. Yeah.
This is more of, again, a meta question. So I really like the second study. And I was just wondering, so you work with GPT-2 and Llama 2. That is when in the pre-training, we were using a lot of like unstructured data. But now the more models that we have, like latest versions of Llama and Qwen 3, they've now started throwing the thought traces in the pre-training as well. So what do you think of, like when you throw in a lot of thought traces in the pre-training, like you mentioned, language and thought are not processed in the same way. What do you think would be some open questions for that kind of study, where you're looking at models that were also pre-trained, like they do an expert prediction on the thought traces?
Yeah. I think it would be very hard to tell. They're also much bigger. And so I think they will represent event roles much better, but I don't know if it's because of the size or because of the corpus or because of some combo. Because it seems, just in general, it seems like just scaling up the models gives them all these abilities that GPT-2 was like really bad on or bad at. And so scale matters regardless of the corpus. I think the thought traces would help a lot with the reasoning. I don't know if it would help with this specific thing, but yes, it would. I think it would help a lot with the reasoning, because I think a lot of what LLMs do with complex reasoning is sort of just predicting the next step, right? And once you predicted the next step, you can predict the one next step. And so if you get examples of how to break the problem to the first step and then the second step, I think that might help you a lot. Yeah, get a lot of these thinking aspects. Yeah, but I also mentioned in general, the more structural cues you have in the input, right, it'll be easier to learn. So for example, in languages that are not like English, you have case marking, which are these small morphemes that you add to a word to say that's the agent, that's the patient. And it often happens in words where in languages where the word order is flexible. So you can put the agent first or the patient first, and there aren't that many rules. And so to help the listener, you put these morphemes. Like those, if you train an LM on those languages, it has to be good at, right, at agent versus patient, because you have those sub tokens, right? Those like morphemes to tell you this is the agent, that's the patient. So I haven't tested it, but like, how could they not? Like for sure, we'll find it there. So I think the more structural cues you have in the input for that or for other types of reasoning, the better you'll be. All right, it's late, so you should all go home or back to the lab or whatever. Thank you. Have a good weekend.